In question 3 in exam 4, we have a 1.0 kilogram ball and a 3.0 kilogram ball connected by a 0.80 meter long, rigid, massless rod. The rod is rotating clockwise about its center of mass at 20 RPM. Part A of the question asks you to draw a sketch of this system. Then calculate the location of the center of mass in SI units with respect to the smaller ball and with respect to the larger ball. So let's do that. Here's the small ball and the large ball located at a distance L from the small ball. And the center mass is going to be located somewhere between the middle of the rod and the location of the large ball. So it's going to be over here someplace. And then if we ask what is the center mass of this system with respect to the location of the small ball. In other words, what is X center mass in this figure? And let's call this big M, and we'll call this little m. And this distance is L, separating the two masses. Then X center mass, and this is part A, X center mass with respect to the little ball is equal to big M times the length, the distance of separation, big L, over the sum of the masses in the system, big M plus little m. Big M is 3, and the sum of the masses is 3 plus 1, or 4. So the location of the center mass is 3/4 the length of separation, or 3/4 times 0.80 meters, or 0.6 meters. And I could denote this as X center mass with respect to little m. X center mass with respect to big M is just equal to L minus X center mass with respect to little m, or 0.2 meters. And I'll go ahead and call this X2, and I'll call this X1. All right. So that's the answer to part A. And part B, what is the moment of inertia of this system? Well, with respect to the center mass, the moment of inertia is equal to little mass times its distance from the center mass, which is x1 squared. And then the moment of inertia to the big mass is equal to its mass times its distance from the center of mass, x2 squared. So if we calculate this, this is equal to little m, which is 1.0 kilograms, times 0.6 meters squared, plus big M, which is 3.0 kilograms, times its location with respect to the center of mass, which is 0.2 meters squared. And we put that in our calculator, and we get a result 0.48 kilogram meter squared. In part C, a constant torque is applied, causing the spinning to stop after 6.0 seconds. What is the angular acceleration during this time? If we have a constant angular acceleration, then this is given by the change in angular velocity divided by the time interval, delta t. So this is equal to the final angular velocity minus the initial angular velocity over delta t, which is equal to 0 minus (20) RPM converted to radians per second over 6 seconds. And I'm going to insert a negative sign in here because this is a clockwise rotation. So our initial angular velocity is negative 20 RPM. So we're having a minus times a minus. So we end up with a plus in the numerator. And this is 20 revolutions, or 2 pi radians, 20 times 2 pi radians. Over 6.0 seconds. And then we need minutes in the denominator. So we have a factor of 60 seconds in the denominator. And this results in an angular acceleration of plus pi over 9 radians per second squared, or 0.349 radians per second squared. Then in part D, let me put a block around our answer for C. In part D, what is the torque that was applied? Well, the angular or rotational analog to Newton's second law is torque is equal to the moment of inertia times the angular acceleration. So we simply put in the results that we got from part B and C. So for the moment of inertia, we have 0.48 kilogram meter squared. And for the angular acceleration, we have 0.349 radians per second squared. And when we multiply that out, we see we're going to have kilogram meters per second squared, which are newtons, times meters, which are the correct units for torque. So let me put, and the result is 0.168 Newton meters. And that concludes this review of question 3 in exam 4.